Okay, so hello everyone again. And we are ready for the second paper of this session. So Alessio, I guess you can put your presentation in the screen sharing. So yes. The second paper of this session is entitled Model-Based Automation of Test Scripts Generation Across Product Variants, a Railway Perspective. It's from Alessio and co-authors. And this paper puts together 3 authors from the Bombardier Railway Transportation and the 3 authors from academia, which is a really nice collaboration. So unless you have a total of 30 minutes for your presentation and the Q&A session, so please try to leave 5 to 10 minutes to the questions, okay?
Yes, please. Thank you so much, first of all, for the introduction, and please feel free to interrupt me or just give me some signal if I need to speed up. Right now, I cannot see the cloud screen, so even if there are questions for me or so, you can ask me directly or read them for me. That would be very great. So thank you again for the introduction, and yes, it's a pretty long title and a pretty long list of authors as well from different organizations and a couple of nations, actually, so Sweden and Italy, basically. And as you can get from the title, we are gonna look at the work we did for automating the generation of test scripts in the context of software product lines, and specifically in the railway domain. So as you heard, this work was done in collaboration with one business partner, which is Bombardier Transportation, which very recently was bought by Alstom. So it's, anyhow, we don't care much about the ownership, but when we started this collaboration, what we realized is that Bombardier, as many other companies, basically, started to use always more extensively the software product line as a method for developing their product, right? And as we know, software product lines have a lot of benefits, a great deal of benefits, but they also come with some challenges. And this research, of course, will look at one of the challenges that Bombardier had and also how we solved. And we will do this by leveraging, let's say, a running example, a real use case, which basically is the Aventra software product line, this Aventra family, which is actually a family of train that is currently being produced from Bombardier Transportation. But before to go in that detail, I very generally want to say which was the problem that we tackled, that we addressed. So let's say in this case the Aventra family is a family of 5 trains developed or designed for the British market, and these trains clearly have very many similar or common features, we can say. So from very simple to more advanced one. And this, for instance, like the train, the TBC function. So, and this function from a general, or in the paper we use the terminology from a functional perspective. They have, let's say, they behave pretty much similarly. So they have the same steps, the same logic, and so on and so forth. However, the implementation of this function in each product may differ, and actually differ, for a number of reasons. And the main, let's say, reason is that, for instance, the trains have different underneath hardware platform. So this platform may be more or less complex, may be leveraging different signals, actually. And then, of course, the, let's say, functional or logic signal is hence implemented by different concrete electrical signals with different steps and so on. So in Bombardier, what they experience is that when they had to develop some, let's say, very technical and concrete artifacts, such as the code, or in this case, the test scripts for the trains, they couldn't basically take advantage of the reusability aspect brought from the software product line. So what they did before our research was to create, let's say, one test script for, let's say, one train, one product. And then they were using the so-called opportunistic reuse strategy, which simply meant that they were copying the same test script for the other products in the family, and then they were manually changing the let's say signals which were different in the product. So it might be the name of the signal, the number of the signal, the interaction of the signals, and so on and so forth. And so that was the strategy. Clearly, this strategy or this way of proceeding had some drawbacks. First, it was the effort that was required. So clearly, manually modifying artifacts is undesirable, and for industrial product family is sometimes even unfeasible because you have a lot of products. You have a problem with when it comes of error proneness, in the sense that since you do manual changes, you might be more likely to introduce errors and to propagate eventually errors, and also consistency. Because different changes, manual changes may not be propagated correctly between the test scripts, or between the test scripts and the more, let's say, functional, more general artifacts. So our research looked at this, let's say, problem, and of course try to contribute. And specifically, the way we contribute is by using well-known techniques, software engineering techniques, mostly model-based techniques, for building a lightweight, we call the lightweight approach, which is composed by the following, let's say, main ingredients, as you can read. So I hope that you are more or less familiar with the concept of model-based development, and I won't go into the details of this model-based development and related concept due to the lack of time. If you are curious and you don't know much, you can always contact me or any other authors later. So in general, what we did is we developed a set of languages, we can call, that could allow us to solve this problem. What we thought is to develop, first of all, a small language that could be able to represent the feature of the family from a functional point of view, a language that could be able instead to represent the feature in the way they are actually implemented on the trains, so in terms of specific trains and signal. Then a language that could help us in tracing the relation between the actual signals in the trains and the more, let's say, functional or logical signals as they are specified for the common feature. And then a small language that could help us for with the specification of test cases, general test cases. And another ingredient that is an automation mechanism that we call model transformation. It's typically called model transformation, that basically was putting some of these elements together for generating the final test scripts that we then run and use for the actual products. So later on, I will show you better like how these pieces come together, and we will look at a concrete example. Beside the proposing this, of course, lightweight framework or approach, we evaluated it upon this Aventra software product line, as I mentioned earlier. And also we, and doing that, we kind of, let's say, evaluated the applicability of the approach, but also how the approach was able to reduce these problems of the opportunistic reuse strategy that I just mentioned earlier. And we also basically try to assess or have an indication of the relevance, industrial relevance of the work that we did by using a focus or expert interviews, where we basically got collected feedbacks from the Aventra integration team. So right now I will show the architecture, we can say, of the proposed approach, and this figure puts together all the, let's say, contribution that I mentioned earlier. And right after this, we will show, and I will discuss a little bit the application of this approach on the Aventra use case. But before doing that, I just wanted to recall once again the contributions and put them in the context of the approach. So this is the general model that allows you to basically defines the function of the functional services of the software product line. And of course, you use we developed this language, and this language is used for producing a model. Then we have this other language that, as I said, is able to describe the functions of the train, specifically for a given product, so in terms of signal and so on. And again, this is the language that we develop, and this with this language you create a model. Then we have this other language that, as I said, help us in relating this information. And once we have all this information in place, what we do is that we create general test cases. These test cases are created basically taking into account the general, let's say, model over here. And then this transformation consider the information specified in this model and is able to translate basically the general test cases that we wrote in a set of concrete test scripts, one basically for let's say for a single test case, you will have a set of different test scripts, one for each product in your software product line. So yeah, let's see the application of or let's discuss a bit the application of our approach in the Aventra use case. As I said, the Aventra use case is a family for of passenger trains for the British market. It consists of 5 trains, or it consisted, at least when we did this research, of 5 trains. And as I said, there are different functionalities. I mean, tons of the functionalities that are common. So according to this, of course, the approach and the steps, the first step that we need to do is to model the general, let's say, software product line. And so that's the resulting model. This model, as I said, is created using the language that we basically that we created. Okay, so here this is only a piece of the model. As you imagine, the model is pretty big. So, but in general, we can see that we have the family, and then we have all the functions that are common for this family, and for each function we have the different inputs that are used, let's say, from a functional point of view. Okay. The second step of the approach is to instead model the specific, basically, products and the specific signals of the products of the trains. And again, we did this using the language that we developed, and this is a piece of the model for the Aventra family. Here we only see, for instance, 3 trains, and then we only see few functions for each train. So in this case, we can see that we have the activate cab function that is specified both for the EAA train and for the lot and for the SWR train. But also then we can see all the specific signals that are inside each and every product, inside each and every train. So to understand this better, we can actually look at this picture or this slide over here. And here you can see that, for instance, the same function, I mean, this is another representation of this model. So here what you can see is that the specific function, the general function activate cab for the EAA train, for that specific train, makes use of these basically signals, so input and output, right? While the same function for the LOT train use different signals, and again, the same function for the SWR use different signal, different both like the names and for instance, in this case, the number of signals that are used. Okay. So by having this model over here, we basically can see which are the function in the specific signals that are involved in each and every function of that train. So the third step is the linking of this information, right? So what we do is we do this linking using, as I said, the language that we developed. And the language is pretty much, in this case, easy, and it allows you to create links, basically. And each link, for instance, if we examine this, then you can say, you can see that here you have that the general function activate cab is actually related to the specific function, so to the specific implementation, activate cab SWR, LOT, EAA, and so on. And here, of course, this is another example for the other function, but also you see that here the generic, let's say, signals, so these signals over here, are linked to the specific signals, so to the signals of the train. Okay. So once we have this, we are almost done, because what we do is we create general test cases in this case, and this test case is created again with the language we developed. So this is the syntax was basically created by us, and these test cases are defined on the, let's say, general model. Okay, so if you see over here, the signal are the generic one, which I reported here just to make it clear. So in once we have basically these test cases written, what we do is that we run the automation mechanism that again was let's say an artifact that we developed within this research. And the transformation, what the transformation does is that it takes the information specified, essentially the models and the test cases, and generate the test scripts. Okay, the test scripts look like something like this, and what you can see is that basically this from the general test case that we wrote in the step before, we created these test scripts where the general signal are replaced with the concrete signal for this train, let's say, while the operation on the signal stayed the same. So this is, again, is just a small example of the test case, and this is only one test case, but again, one test script. But again, we produced, or the transformation produced, one test script per each product per function. So, so this was like more or less in like a summary of the approach and how it worked and how it works and what it does. And as I said, we try to also check whether this approach could solve a little bit the problem that were identified at the beginning of this research. So in general, when it comes of the effort, we measure the effort, and you can read the way we measure in the paper. But what we basically saw is that for already relatively small software product line, our approach required less basically number of manual artifacts. So the manual effort is lowered, and again, you can read the calculation in the paper. When it comes of error proneness and consistencies, basically we these aspects are mitigated by construction, because we don't basically do manual modification. Everything is beside the models. Everything else is generated automatically. So as long as what you model is correct, what you get generated is correct, and you don't even propagate the possible errors, let's say. Consistency between the general and the concrete artifacts is again achieved by construction. Although, of course, if you one thing to say is that if you basically modify the models, clearly you need to run again the transformation. Otherwise, you will have artifacts that are out of sync. We also try, of course, what we did is we also saw if what we were generating was actually could be basically executed. And yes, we executed the test scripts in the Aventra testing environment. But we also wanted to check if the test scripts that we generated were different from those that were manually written. And besides some comments that we put during the generation phase, for the actual commands there was no difference. If I have like last minutes, I would just say that as part of the evaluation, we also asked basically the practitioner, the engineers from the Aventra team, to some question to understand the relevance, industrial relevance of the work. For doing that, we use a model that was proposed in a research paper some years ago. You can read about it in our paper as well, and we got pretty positive response. And the general highlighted that clearly the problem was relevant for them, but this partially we also knew, because that was the main reason why we started the research. But also that the solution that we found was basically relevant, and that the settings that we use for running this research was industrially relevant as well. So I hope I didn't exceed my time, and that we left decent amount of time for the possible questions, if you have any. Yeah, I just want to thank you for the attention and for being here.
Okay, so thank you very much, Alessio, for the really nice presentation. We still have a couple of minutes to some questions. So we have one in the chat from A2. So let me start with this one. So the question is, what notation did you use for defining the common and variable features of the software product line? If it wasn't feature models, was it because feature models had some sort of limitations, for example?
So as I said, the notation, I think that the question refers to the language. This is we developed this language using eCore within Eclipse. So this is completely like a language that we came up with. The reason are mainly for simplicity, because like this we could basically be sure that we were representing only the information that we wanted, and we were not having other let's say other elements that were not needed at this stage. In general, we use feature models, or Bombardier uses feature models even within some tool, for instance, feature ID, that we also used in our related research. But for this, we just developed our own languages.
Okay, thank you. So do you have any other questions from the audience? Okay, if not, I have a couple of questions here, so let me start with some of them, so maybe the audience will start asking questions. So you mentioned in the paper that you are working on further extensions to enable the automatic generation of different development artifacts, right, besides the test scripts. So what artifacts are you referring to?
Yeah, so in general, as I said, because this research was very much done in collaboration with the testing team, but of course, even let's say the specific the methods, the software that actually runs on the on the trains have the same or might have the same issue. So we were thinking to use the same approach for generating all this, in this case, these pieces of software, and it's like methodologically won't change much, but we basically will need to change the transformation and the language, the DSL basically. I can show you here. Or maybe here we can reuse something like maybe even now I don't know, but maybe if they use some UML or whatever diagram, we can use also that kind of information.
I see. So there's another question from the audience. One question from Rodrigo, and he would like to know how you derive the automatic test scripts.
So what do you mean? How you derived?
The automatic test scripts.
No, yeah,
and I guess
that I understood, but I was just asking if we could have some more details. I will start giving some answers, and then we can basically you can tell me if I answer your question or not. So the transformation is done using XLEO. Which is a model-to-text transformation language, to be extremely precise. And so what the XLEO use a template. It's a template-based language, which means you have, let's say, in the transformation that we wrote, we have part of the text that are basically fixed, and then we have some, let's say, part that we can say are sort of placeholders, and this placeholder will be changed according to the information derived from the model. So in this case, for instance, the transformation would, just to have an example, the fixed part would be public void, let's say, and this name over here would be changed according to the function, the same with for the name of the signal, while the let's say operation on the signal and so on stay the same. I hope I answered to
Yes, so I guess Rodrigo is curious if you used some tools or frameworks. So I guess you developed your own approach, right, and packed everything together in some sort of tool?
Everything is developed within Eclipse modeling framework. So the languages or metamodels are eCore developed using eCore. The transformation is developed using, as I said, XLEO, and the language, also is developed using Eclipse modeling Eclipse modeling framework. So.
Okay. So we have about 1 minute. So the last question. So maybe I'll go for this one as a follow-up of what Rodrigo asked. So you noticed that you have a GitHub repository available. So is part of the material that you produced available over there? Could it be reused by other researchers?
Yeah, I mean, I think, yeah, okay, it can be reused, but clearly you will need to customize. But the idea is that I think that my co-author Fabio put everything on the GitHub, so you can first of all download Eclipse modeling framework, import the project, and run it yourself to see that works. And then clearly you can also use it freely as a base for your research.
Okay, perfect. Thank you very much again, Alessio, for the
No
very nice
problem.
presentation. Let's move to the next one.